Okie dokie. So this is the third and last portion for this week. It's going to be about an Otto cycle. So an Otto cycle is slightly different from the other two cycles we looked at. An Otto cycle is going to be a single closed system. So it's to model a four-stroke engine. So essentially, it's just going to be one piston that we're bringing through 4 phases. It's not 4 different components in the same cycle. Okay, and it's a gas power cycle. So essentially, I have this one piston, and from 1 to 2, it's a compression stroke. So I'm building up pressure. From 2 to 3 is ignition. So while that pressure, that volume is being maintained, I'm igniting it. After ignition, from 3 to 4, I am expanding the gas. And then from 4 to 1, I am cooling the gas. So if you look at what this looks like on a PV diagram, I have it here. You have the diagram, you have the list of steps here, but essentially, while we're igniting and cooling, we're maintaining a constant volume. We're modeling it as 4 distinct separate steps. It's not totally 100% the case if you talking about real car engines today, but it's a good enough approximation for what we're going to be doing. The compression and the expansion steps are going to be polytropic. It's listed in the question, and so I rebrought these equations down here. We're going to need them. So let's have a look at, one more thing is the compression ratio. So we're always comparing essentially the large specific volume. This is not correct. So hang on. No, this isn't correct. The compression ratio is the large. It should be greater than 0. Yes, it should be greater than 1. And it's the large specific volume. So here 4 and 1 or 4 over 2 and 3. I had written it backwards. So it's a value greater than 1. So let's take a look at this specific question. So it says that an engine with a compression ratio of 9 is running with an air standard Otto cycle. So that's telling us the gas we're using. Prior to the compression process, which is polytropic with the N or with an N of 1.4, the air is at 100 kPa, 32 degrees C, and 600 centimeters cubed. Temperature at the end of the polytropic expansion process is 800 Kelvin. Determine the highest temperature and pressure in the cycle, the amount of heat transferred in kilojoules, and the thermal efficiency. So if we look at what's given, we're given a lot of information just before the compression stroke, right? We're told prior to the compression process, we have all of those values. So I'm just going to start by listing them. So at stage 1, I have a pressure of 100 kPa. I have a T1 of 32 degrees C, which is 305 Kelvin. And I have a volume 600 centimeters cubed, which in meters cubed, I'm going to need it in meters later, is going to be 6 times 10 to the minus 4 meters cubed. I'm told also that I have a compression ratio of 9. And gas-related stuff, we need the R value, which I took from the package. It's from the properties of gases. And it's not a C, it should be a CP. Oh no, it's a CB. All right, so this is everything I know about the gas. So to find Tmax, which point, because we're asked to find the highest temperature and pressure. So the highest pressure, if we look at the diagram here, is going to be 0.3, and it's also the point where we would have the highest pressure. So I'm going to write it here. Highest temperature and pressure. If you think about it, it makes a lot of sense. So I've compressed my gas and I've ignited it. I've put in a lot of heat very quickly and have yet to allow it to expand. So that's the point where we would expect to have the highest temperature and pressure. How am I going to find the highest temperature? That's pretty easy to find, actually, because I know my compression ratio, right? And my compression ratio is I'm going to rewrite it as I'm going to look at it from here. So it's V4 over V3. So what I'm going to start by doing is I'm going to start to find my highest temperature. So from the polytropic equations, I see that T4 over T3 is V3 over V4 to the K minus 1. So this is for highest temperature. And this T4, I know T4, it was given to me in the question. At the end, T3 and 4. So I'm looking here at the, I'm looking at the expansion process here. I'm given the value at the end of the expansion. So I'm told that T4, this is another value that I have. So I'm told that T4 is 800 Kelvin, I believe. Yeah, so after the expansion process, we have 800 Kelvin. Knowing that this expansion process is polytropic, I'm just going to work backwards to solve for T3. That'll answer the part of the question for the highest temperature. T4 was 800 Kelvin. T3 is unknown. V3 over V4 is 1 over 9. Okay, because my compression ratio is always the large value. So this one over this one. Okay, and this relationship from the polytropic process is V3 over V4, which is the reciprocal of my compression ratio. And if I isolate for T3, T3 is going to give me 1926.6 Kelvin. So I was able to find highest temperature. That was easy. Oh, I didn't? Oh, I missed solving for the highest pressure. But the highest pressure is fairly easy to solve for. Knowing, of course, that the cooling state, okay, we'll solve for the pressure now. So it's going to be this one. I had missed that one when I did my calculations earlier. But let's be thorough here. So I'm asked to find highest temperature. Now I'm going to find the highest pressure. So I have this relationship here for the highest pressure. So I'm going to again relate 3 and 4. Draw, please. Okay. Did I do that correctly? Yeah. Okay. And P4 is known because I know that P1 and P4 are equal because the cooling is because the cooling and heating processes happen at a constant pressure. I know that P1 is going to be, that P4 is also equal to P1, right? Because the cooling happens at a constant pressure. So I know that P4 is 100 kPa. I'm asked to find P3. I know my T4, I just had it. It was 800 Kelvin, and my T3, I just solved for it. And this is going to be 1.4, yes. 1.4. 1.4 divided by 0.4. And if I do that math, I will get a P3 of 2,167.5 kPa. All right, so that answers the part asking highest temperature we got, highest pressure we got. To find heat transfer, now the amount of heat transfer is going to be a little bit tougher, right? Because we need to find, basically, we're asked to find our Q in and our Q out, okay? And how are we going to do that for the gases, for the closed cycle? Is I'm going to use my CV values. I'm not going to be using enthalpies. I don't have tables to pull those from. So I'm going to have to solve for all of the temperature points. So I have T2, no, I have T3, and I have T2. No, I have T1. Yes, in the question I had T1, and I have T4, which was known. T3, I calculated it. And I'm missing T2 in order to do that. So what I'm going to do is I'm then going to use the compression stroke, and I'm going to calculate my T2. So, so this is over my compression stroke. I need to solve for T2. So that relationship, we've already used it. T2 over T1, V1 over V2, K minus 1. So I get that T2 is equal to T1, which is 305 Kelvin. V1 over V2 in this case is equal to my compression ratio, which was 9. And then 1.4 minus 1 gives me a T2 of 734.5 Kelvin. Just this is equal to compression ratio, and this was equal to 1 over compression ratio. And so I'm also going to need the mass in order to find total, right? Because if not, I'll be getting values in kilojoules per kilogram, and that's not what I'm looking for. So what I'm going to do is I'm going to use all of my information at state 1, because state 1 is the only one where I know the volume. So I'm going to just do the ideal gas law real quick. So I know P1, V1, MRT1. And everything I have is known. So 100 kPa. My volume was 6 times 10 to the minus 4 meters. My R value was 0.287. And, okay, let me do that properly. Kilojoules per kilogram Kelvin. And then my T value is 305 Kelvin. And this will give me a mass of 6.85 times 10 to the minus 4 kilograms. All right, now I'm going to be able to look at 2 to 3, which is going to be my Q in. So this is my ignition state. So if you look at our second law equation, right, we have delta U Q minus W. And we know that there is no work being done during the ignition. Right, and there is no flows, right? There is no flows whatsoever because there's no gas coming in or out. The gas is contained within the piston, and we are expanding and contracting it in 4 steps. But nothing is flowing in the Otto cycle. That's what makes it different from the Rankine and the Brayton cycles. You know there's no work done during ignition, so therefore Q is equal to delta U. And what did I say about delta U? For gases, it's mCV delta T. And for this, for the ignition state, that's mCV. Ignition is from 2 to 3. Yes, from 2 to 3. So a delta will be 3 minus 2. Mass, I just calculated it, 6.85 times 10 to the minus 4 kilograms. My CV was 0.718 kilojoules per kilogram Kelvin. My delta T is 1926.5 Kelvin minus 734.5 Kelvin, which will give me a Q of positive 0.5866 kilojoules. It's what we would expect, right? This was our ignition stage. This was positive. So it's a Q in ignition. So this is our cooling. And again, same thing with ignition, right? With cooling, there's no work. So Q is going to be equal to delta U, mCV delta T. And if we look at our cooling stage, our delta here is going to be from 4 minus 1. Sorry, 1 minus 4, because our steps go in this direction, and our delta is final minus initial. So it will be T1 minus T4. And I have all of these values. So 6.85 times 10 to the minus 4 kilograms and 0.718 kilojoules per kilogram Kelvin. And then my delta T, 305 Kelvin minus 730 minus 305 minus 800. Which will give me a Q of minus 0.2435 kilojoules, which is what I would expect. Now, if we look at 1 to 2, 1 to 2 is our compression stage, right? Because we're asked to find, why are we calculating? We need, okay, because we're going to need the work net in order, because we're asked to find thermal efficiency. So actually the next step is amount of heat transferred in kilojoules. We can answer that. So amount of heat transfer is going to be Q in plus Q out, which is 0.5866 kilojoules plus a negative 0.2435 kilojoules, which will give me an amount of heat transfer of 0.3431 kilojoules. All right, so that's that part of the question answered. Amount of heat transferred, and now thermal efficiency. So for the efficiency, right, we were talking about it before, we need the work, we need the useful quantity we're getting out of it. So now we're going to have to consider, our compression and our expansion phases. So 1 to 2, I could label these correctly so that we're all on the same page. Ignition is 2 to 3. Cooling is from 4 to 1. So now we're going to talk about 1 to 2 was compression. Yeah, compression. And that is if I look at, again, my first law equation, delta U Q minus W, I'm having no Q, right? All I'm doing is work. So therefore, I know that my work for my compression, which is 1 to 2, is going to be equal to negative mCv T2 minus T1. And now if I do the math, I'm going to see it's a negative 6.85 times 10 to the minus 4 kilograms times CV 0.718 kilojoules per kilogram Kelvin. And then T2 minus T1 is going to be 734.5 minus 305 Kelvin will give us a work of negative 0.211 kilojoules, which is what we would expect, right? Because for the compression, I am applying a pressure on the gas I am applying a force on the gas to increase the pressure. That's good, compression. And now we're going to talk about expansion. So it's going to be the same thing as the compression. So I know my delta U is Q minus work. There's no work. And so therefore I know that my expansion is operating from 3 to 4 is a negative mCv T3 minus T4. From 3 to 4, so it's T4 minus T3. And all right, and this will give me a negative. Again, it's a little bit repetitive. So 6.85 times 10 to the minus 4 kilograms, 0.78. And then my T4, 800 Kelvin minus 1926.58 Kelvin gives me a work from 3 to 4 of positive, which is what I would expect, right? The gas is allowed to expand, so it's work being done by the gas onto the piston. So I get a value of 0.5541 kilojoules. So now I'm going to calculate my work net. Is going to be my work from 1 to 2 plus my work of 3 to 4. This addition here is extraneous. So it's just the sum, which will give me minus 343 kilojoules. So I can write the intermediate step there. I'm skipping steps, but it should be 0.5541 kilojoules plus a negative 0.211, which will give me 0.343 kilojoules. For curiosity's sake, could this value ever be negative? In theory, if my absolute value of the work needed for the compression is greater than the work I get out of expansion, the value would be negative. But that's a totally useless cycle. It means that as a net, I am putting work into the system, which is not useful by any means, right? The whole goal of this cycle is to create work. So next is going to be thermal efficiency. So I'm going to see that my thermal efficiency is, as before, my work net over Q in. My work net, I just calculated it, 0.343. And my Q in, I had calculated it up earlier as 586.6. Gives me 54.5